All right, good morning, or good afternoon, good noon, I guess it is. Welcome to week 13 of Issues in Environmental Science. And this week we'll be talking about climate change. And I'm not sure how much time we'll be able to cover in the two lectures, but what I want to talk about initially are climate cycles over differing time scales, because when we look at climate change, one of the concerns is that this is a cyclical process, that there's a cycle of climate change, and that what we're seeing, the changes that we're experiencing now are part of a natural cycle. And so that if we just wait, things will shift back to the way they were. There is some validity in that, but it's very important to consider the timescales. And we want to look at the measurement and prediction of climate change at various timescales. And then, of course, the greenhouse theory of atmospheric forcing. So the idea that by changing the constituents of the atmosphere, particularly by increasing CO2 and other greenhouse gases, we're driving the process of global warming through a phenomenon known as greenhouse effect. So we want to look at that in detail. And then we'll be exploring the human impacts of climate change, the way in which in recorded history and previous history, we can see how changes in the climate have had an effect on human population and society. And we'll delve a little bit into climate politics. One of the things that I would like students who've taken this class to be able to do when they go forth into the world is to make cogent arguments about climate change. This is a major issue. It's not as big as the COVID pandemic that's occurring right now, or it's not as acute perhaps, but it's every bit as existential in terms of the future of society and the way in which we're going to be able to live our lives in the decades to come. And so when you go out into the world and get a chance to talk to people who agree or disagree with you, I think it's important to be able to make arguments and present the evidence and data about climate change in a organized, consistent, factual way, so that to the best of your ability, you're able to influence the way people are thinking. So I'd like everyone to have some good arguments that discuss the validity of climate change, the phenomenons that are associated with it, and how we can understand that. And then at the end of the lecture material, we'll look at a modeling study, which I think is really important for understanding the greenhouse effect, and particularly what's the atmospheric forcing factors or the warming factors of CO2 and how this functions, because one of the features of CO2 is that it's present in really trace amounts, parts per million in the atmosphere, and yet we're very concerned about the way in which this gas affects climate. And modeling studies explain the feedback mechanisms by which CO2 first raises the temperature, and that increases the amount of water vapor in the atmosphere. Water vapor is also a greenhouse gas. In fact, it's the major greenhouse gas. So there's a feedback loop between the amount of CO2 in the atmosphere, the amount of water vapor, and the amount of warming. And so modeling studies can help us to understand that. All right, before we go into that, I got a few housekeeping details to present. So this will be the last week that I'm doing lectures. Starting next week, the class will be devoted to team presentations. I believe we have enough time left so that each team will have 20 minutes for questions, 20 minutes for presentation, followed by 5 minutes for questions from the audience and from me. And that will allow 3 teams per week, per session to make their presentations. So Carrie will be setting up a sign-up sheet for the presentation slots, 3 per class, and you want to go ahead and sign up. Now, we want to look out for some of the teams who have team members who've unfortunately had COVID, they've tested positive, and they've reported with serious symptoms, which as we know, COVID can be quite debilitating, and even for young people. And so a couple of teams have been impacted by that, and we want to let them go last in the process. So the final, the slots on the final day of presentations will be for people who have been, or teams that have been granted an extension. So don't sign up unless you have a team for the last day, unless you have a team member who's come down with COVID, and so you need a little extra time to get your presentation organized. I've been having sessions with people. I think we've gotten through, I think there's one more session scheduled. So all the teams should have had an opportunity to meet with Carrie or with me to go over their presentation and their report, and hopefully get some pointers on how to make that report into an excellent contribution or submission for your team grade. Now, one other requirement that I'm going to impose here is that each team needs to compose 5 multiple choice questions based on the material in their report and presentation. And these 5 questions, so that'll be 15 questions per class, 30 questions per week, and that will be the weekly reading quiz will be over that material. And I'll have those quizzes will be due at the end of the, well, I'll change the due date so that everybody has time to respond to that. But that means that you do need to be able to listen to the lectures and the presentations by the other teams in order to be able to answer these quizzes. So it's important that you do that in order to get credit for the quizzes. Okay. And I guess this is sort of leading up to, final exam thoughts. I've been sort of mulling over what kind of final exam we should have. I'm going to keep the structure, I think, similar to what we've done in the past. But we're quiz questions from the reading quizzes, and then from the quizzes that are the questions that the teams come up with. That'll be a major part of the final exam. But I also want to bring into the exam material based on what I've talked about in my lectures. So my lectures, you have notes that you can look at, and hopefully you're attending class, taking notes, and learning something from what I have to say, and you'll be able to answer multiple choice and or essay questions based on that material. I also would like to ask some thought questions that will require research and analysis. And, by which I mean I might assign you a question for which you'll have to go and do some research in the primary literature, and then thinking about the research that you've done to come up with a plausible answer and response there. Okay, so that's the sort of housekeeping. And before I start with the lecture, are there any questions about where we're at in the class or the exam or presentations or anything that we need to know? So please.
Dr. McDonald?
Yes.
This is Darren. I was wondering if the final exam is going to be on a particular day, or are you just going to give us a certain amount of time to complete it?
I think I'm just going to give you well, it'll be on a certain day. Yeah, I'll assign it, but you'll have multiple days. You'll have, for the quiz part, you'll have the question part, you'll have, a period of time to answer the questions. And then for the essay and longer answer questions, there'll be a longer period for that.
Okay.
Okay. Any other questions? So I'll just say, that I've conferred, I guess, with 7 or 8 of the teams, and by and large, the progress that I'm seeing looks promising. Sort of different levels of completion by the different teams that I've seen. I think some consistent themes or issues that I'm seeing are, designing your presentation slides so that you are making use of graphics and tables and figures, not as sort of eye candy, but as a way to convey information. And hopefully the slides that I show you and the way that I organize my slides can serve as a model for what I hope is an effective means of presenting information. And you'll see, in the slides that I show, typically I don't put a lot of text on the slides. the exception being, these housekeeping slides where I have specific ideas that I'm trying to get across. But typically what I'm showing in the slides are data, trends, maps, graphs, pictures, illustrations, cartoons, that sort of thing. And these displays offer some specific quantitative findings, or highly qualitative specific sorts of findings that I then talk about and try to explain to the viewers, that's the students, and that this material comes across clearly in that way. And I think what you really want to avoid are slides in which there are a big block of text, that people have to read through, because that's, if you as a presenter just sort of stand there and read that material, that's not easy for an audience to follow. And if the audience has to read the material while you're talking about something else, that can be very distracting. So try to keep your text large and legible. Try to keep your figures large and legible. You really want to avoid squishing things down so much that they're difficult to see, because you remember that people are looking at this on a relatively small screen, their laptop or their home computer. Hopefully you're not trying to follow along my lectures on your phone, unless that's absolutely necessary. It's still a small screen. You have to keep that in mind when you're thinking about how large the text is and at what scale to reproduce the drawings and the graphs, etc., that you're using. Okay, no questions? Everybody's clear? Okay, very good. So let me go over climate change issues. And here are some different thoughts or different topics about climate change. The first thing is, this concept of climate versus weather. And I think probably most of you all understand that. But we need to be clear when we talk about weather and climate that we're talking about similar observations, the amount of the temperature, the amount of precipitation, the humidity of the atmosphere, the wind, etc. Those are all part of this larger global environment, which we can measure meteorologically or oceanographically. Climate is the long-term average of the weather. So weather prediction starts to really break down, after 3 or 4 days or a week. So because the way that these variables are so complex and so variable, that it becomes difficult to predict, what the weather is going to be, even if several days in the future. We've gotten a lot better at that through models and through a national and global system of observation using satellites at predicting, measuring the weather and predicting how fronts, cold fronts, rain bands, etc., will move across the space and affect different regions at different times. But that's weather. So weather is the high frequency presentation of temperature, rainfall, wind, etc. And climate is the long-term average of those factors. So if people say, well, the climate can't be global warming because it's cold out today, that's a specious argument. It's an argument that has some surface validity, but when you dig into it, it doesn't really make sense. And the other thing, if we're talking about long-term averages, is what is the term over which you are averaging? So there are multiple time scales for considering climate. There's sort of decadal, 100-year, 1,000-year, 100,000-year, million-year, 100 million year time scales. And these time scales are relevant to understanding climate and, in fact, weather, because depending on what the time scale you use, you're going to see different trends, different averages. And there are different factors that control these long-term averages, depending on which time scale that you're looking at. In addition, there are scientific principles that we need to grasp for understanding climate. This greenhouse, the greenhouse theory, which I mentioned earlier, and in the later part of this lecture, I'll go through some of the historical background for the greenhouse theory. Proxy measurements. This is an important consideration because proxy measurements are ways in which we measure one small variable or one minor variable, and from that measurement we can infer what the climate was in the past. And so an example of proxy measurements for climate would be ice cores, and we'll talk about ice cores in a few slides here. But ice cores are ways of the ice cores. By drilling into ice, we are able to get physical samples and chemical samples from the distant past, and so we can measure the properties of those samples, and from those measurements we can infer the information about the larger climate. Isotope geochemistry is a particular feature of all that, something that we do need to understand. I don't know that I have too much in this lecture about isotope geochemistry, but that is the primary technique for understanding a lot of these proxy measurements. Also, modeling and statistics, we need to recognize that statistical understanding or statistical science is a way of knowing, being able to take highly variable observations and infer from these observations what an expected outcome would be. And so statistics gives us tools for doing that. Modeling is another method for taking variables and trying to predict outcomes from those variables. And modeling is a absolutely essential component of climate studies. We understand the Earth system because we're able to build mathematical models that describe in small and manageable ways this huge and incredibly complex Earth system that we live in. Part of modeling are forcing and feedback, the way in which one variable can force others, and how feedback mechanisms make this possible. There's also economic and societal impacts of climate change, regulation, enforcement, lifestyle changes, technological solutions, time horizons. These are all sort of the sort of social background for the human reaction or the societal reaction to these pretty significant changes that are occurring. Okay, so these are all sort of issues and concepts within the larger topic of climate science. Okay, so as we go forward, I'm going to start with the long-term change. What is the big picture, the 100 million year to million year time scale? So what can we understand about Earth's climate by looking at changes using million year, 100 million year rulers to look at how things are changing. And then we'll sort of try to step forward and look at shorter and shorter time scales as we proceed with the material in this lecture. So at 100 million year time scale, and I think I presented this material earlier in the course, what is happening to the Earth that there's sort of an underlying variability in the Earth system that can be understood by looking at changes which are evident when you look at very large timescale differences. And those changes have to do with, at this 100 million year or a million year timescale, have to do with the geologic alteration of the Earth system. Specifically, what I'm talking about is the theory of plate tectonics, the supercontinent or Wilson cycle, which we talked about very early in the course. And what the Wilson cycle is doing is causing the continental land masses to move across the surface of the planet, and in doing so, they move across an ocean background. and I've sort of misstated that. Actually, what's happening is that new seafloor is being generated by seafloor spreading, and as that seafloor is generated, it pushes the continents apart, pushes them around in different directions, and so in the Atlantic Ocean, for example, we get a rifting of the North American and South American craton of the Pangaea, and the Atlantic Ocean opens and forms over 100 million year time scale. Okay, so that's the sort of background process which is occurring over these, very difficult to conceive of geologic timescales. But the consequence for the climate is that we have different a different ocean world, and with that different ocean world, we have we change the way in which heat can be transferred from the equator towards the poles. And that transfer of heat from the equator towards the poles is the sort of critical factor that drives much of the climate. Now, we talked about the properties of water and the ability of water to vaporize and carry with it its latent heat and release it. So typically vaporization is happening at the low latitudes near the equator, and that heat is moving toward the higher latitudes with wind and wind patterns, and also with ocean currents. Well, depending on how the continents are arranged within the ocean sphere, that allows different ocean patterns and different wind patterns to occur. So in a double slice world, there tends to be a lot of transfer of heat from the low latitudes to the high latitudes. So if there's an efficient process of heat transfer from the low latitudes towards the high latitudes, what do you think would be the general trend in global temperature? Warmer or colder? Any ideas? It's hard to get feedback here, but the answer is that it would tend to be colder if the planet would be colder if there were transfer of heat from the efficient transfer of heat from low latitudes to high latitudes. Right. So in a double slice world, we would expect if the supercontinent cycle, the Wilson cycle, had arranged the continents and the oceans in such a way that there was an open corridor between the low latitudes and the high latitudes, we would expect the Earth to be in a relatively cooler condition. Okay? If there's a double slice world with a low latitude seaway, that would tend to allow circulation across the to proceed, global circulation to occur at the low latitudes, and that would generally slow down the transfer of heat from low latitudes to high latitudes. So a double slice world with a low latitude seaway would tend to be warmer than a double sliced world in which that low latitude seaway were blocked by the continents. Okay? And likewise, you could have a double sliced world with high latitude seaways. And so that might produce some sort of middle ground between these two scenarios. Well, have these things occurred in the past? Well, yes, they have. If we look back over time, we can see that in the mid-Jurassic, for example, 175 million years ago, we had a single landmass, the Pangaea landmass, and so that there was not circulation possible at the low latitudes, and heat transfer would have been relatively effective across the remainder of the ocean system, and so that would have produced a relatively colder world. Well, fast forward. So the Jurassic age, despite what you might infer from Jurassic Park, Jurassic Earth was relatively cold, and there were lots of glacial input. Well, with the movement of continents, with the plate tectonic processes, by the mid-Cretaceous, we had a world with the beginnings of a double slice, so that the North American and South American continents had rifted apart. The Isthmus of Panama had not yet closed up, and neither had the Mediterranean Sea closed up across the Asian African connection here. And so there was a mid latitude or low latitude seaway and some blockage towards movement at the higher latitudes. And so the mid-Cretaceous world, 100 million years ago, was much warmer than the Jurassic world. Okay, and so these basic underlying conditions of the thermal radiator, the global radiator, set the background, set the conditions under which Earth's climate plays out. Where are we now? So this is mid-tertiary, about 30 million years ago. So we still have the possibility of circulation. There hasn't been a blockage here. And so this is mid-tertiary world is relatively warm compared to what it is today. And if we want to look back for times in the past when the temperatures were comparable to what we're experiencing now and what we may experience in the coming decades, we have to go back all the way as far as the mid-tertiary, so like 30 million years ago, to find comparable temperatures in the proxy records, which indicate to us what the global temperature, what the global climate was, in the past. And then with the blockage of this mid-continent, mid-ocean passage, because the Isthmus of Panama closed up about 7 million years ago, and likewise the Red Sea and the Persian Gulf was closed, and so the possibility of the seaway was blocked off, and things became cooler. And we'll see as we step forward and look at the long-term climate cycle in more detail that we can demonstrate that there's evidence to show that there was a major shift in the kind of climate that was present. Okay, clear enough? Questions about this? All right, so if we look, so I've talked about, this sort of sweep of history, and I've said that, depending on the stage of, of the supercontinent Wilson cycle, we could have different periods. And so, there have been in the past cold periods, so glacial periods. Remember I said that the Jurassic period was quite cold. That cold period lasted through the mid-Cretaceous, and then things started getting warmer. And so these periods generally here are periods when there have been these open seaways, mid-slice, double slice worlds that allowed heat to be transferred. So we go back 450 million years ago, Ordovician to Silurian. This was a glacial period. Carboniferous to Permian was a glacial period. Jurassic to early Cretaceous, late Jurassic to earlier Cretaceous was a cold period. And the present last 30 million years or so have been a cold period. So when the Isthmus of Panama and the Mediterranean Sea closed off those seaways, we shifted into a mode that allowed the planet to cool off to a level relatively cool compared to the long-term average over the last 540 million years. Why do we look back 540 million years? Because this is what's called the Phanerozoic period of Earth. This is the period in which we've had multicellular organisms, invertebrates, fishes, dinosaurs, mammals, human beings, etc. So that's all that evolution has occurred in the last 500 million years. And over that last 500 million years, we've sort of completed about maybe 2 Wilson cycles altogether. So in the present time, if we look at 10 million year, 100 million year time scale, we're in a relatively cold period, or we have been in a relatively cold period of our Earth history. Okay, is that clear? All right. So how do we know all this? And what material, what information do we base these ideas on? Well, I'm not sure that I have a slide for this, but when we go back into deep time, more than 100 million years ago, or more than 50 or 60 million years ago, the information that we have that we can analyze to figure out what the global climate was has to do with fossil records that we can be analyzed to look at changes in the fossil assemblage that might indicate warmer or colder conditions, and also material that can be analyzed chemically to infer information about what the climate was. That material tends to resolve differences and changes much more coarsely than other materials do. So the further back you get, the less resolution we have for measuring these changes. Now, that resolution, that sort of lack of precision in understanding the rate of change is subject to sort of punctuated events, and we've talked about punctuated events when we looked at the great extinctions that have occurred. And so there was a great extinction that occurred at the end of the Cretaceous period, and that's what wiped out the dinosaurs. So right in here we had a massive change in Earth's history, but it didn't coincide with a huge change in the prevailing climate. That's kind of interesting. And so these glacial periods, or glacial or interglacial periods, these are really primarily driven not by comet impacts or other sorts of things, but by the rearrangement of continents to allow different regimes of heat transfer from low latitudes to high latitudes. Okay, so we can see long-term average, short-term average, that we're going through hot and cold periods, and that we're presently have been in a 50 million year cold period. So if you think 50 million years, what's happened in 50 million years? Well, most of the mammals that we have around have evolved over the last 50 million years. Human beings, primates, have evolved and developed over the last 50 million years. So most of the, a lot of the life on Earth, the ecosystems, the biomes that we understand as being part of the Earth system have developed in this relatively cold period. And so as we emerge from this cold period, as we are presently doing, these systems are entering into conditions that, that are different from those under which they evolved. Okay, so climate proxies. I talked about proxy measurements. Looks like my text has gotten a little squished here, but what this is talking about are measurements that we can make of material that can be analyzed to give us information about what conditions must have been like at times in the distant past. So a lot of what we understand about recent climate change, by recent I mean over the last several 100,000 years, not million years, but 1,000 years, comes from work that's been done on ice cores. What are ice cores? Well, the ice sheets that cover Greenland and the ice sheets that cover Antarctica have been on the Earth for hundreds of thousands of years in many cases, in some cases. So that long period that I showed in the previous slide, that last 30 million years or so of cold in the Earth system has led to the presence of these very, very thick ice sheets. And it's remarkable to think, because we think of ice as being something that, you make in your refrigerator, you put in your drink and it's gone. We think of ice as being this, transient property, this, ephemeral substance. But ice is, in fact, the cryosphere includes material that froze a very long time ago. Well, if that's occurring, how does this ice accumulate? And, so how does that, and how can that, what we understand about the accumulation of ice, help us to understand how we can get information from these cores? So, the way that ice forms on ice sheets is that it precipitates as snow. So every year in the winter months, both in Greenland and in Antarctica, and also in the glaciers and high mountains, there's snowfall that comes in the wintertime. And that snow packs down and forms a layer. Well, if the conditions are cold, that snow that fell in the winter never melts. And more snow falls the next winter on top of that and packs that layer down. Well, that process of snow getting buried under layers of subsequent winter, year after year, creates layers that are essentially annual layers. Now, here's the interesting part. So when snow falls and it's buried under the snow of subsequent years, for a long time, in fact, about 70 years, the air in that snow at the bottom of the pile is in equilibrium with the air of the atmosphere. So the snow is porous enough and there's enough circulation so that there's really no change. If you measured the properties of the atmosphere and then measured the properties of gas that you extracted from snow, there wouldn't be no difference. But after about 70 years or so, this material, and it's called firn, F-I-R-N, so the firn condenses and compacts under the pressure of the accumulating snow, and eventually it squeezes into, stops being snow and becomes ice. And when it becomes ice, there are bubbles of air that are trapped in that ice, and they are no longer in circulation. They are no longer at equilibrium with the atmosphere. And they can be resolved as individual layers in the column of ice that goes down deeper and deeper in the ice sheet. And so here is here's an ice core being extracted from a glacier, probably in Greenland. And then here, this is a picture, sort of visible light picture looking through that ice core. And for scale here, this is about 20 centimeters, so about 8 inches. And so in 8 inches, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 individual annual bands of air trapped in the ice. Okay. So if we drill down and extract that out and carefully extract the gas from these little bubbles and pull it into mass spectrometers and other methods for analysis, we can look at the components of the atmosphere that was trapped in these layers and make measurements, make chemical measurements about its properties. And the principal things that are measured are the carbon isotopes and the oxygen isotopes. And I realized that I probably should have a discussion of oxygen and carbon isotopes, but I think I'll leave that off until Thursday. So for right now, let's just assume that by measuring carbon, oxygen, helium, hydrogen isotopes, we can infer what the temperature was in in the atmosphere across the entire planet. We get some average picture of what that temperature is. And so, just pull back a little bit and think about what's actually going on here. We've got a scientific expedition that goes to Greenland or Antarctica and drills down. Some of these ice cores are 1 kilometer or more. I think the deepest ones are about 2 kilometers down in this core. So if you think about 12 years and 19 centimeters, and the oldest ice cores from Greenland are about 350,000 years, and the oldest ice cores from Antarctica are about 750,000 years. Just a little back of the envelope arithmetic tells you that these cores have to be very long. So what climate scientists are doing essentially is that they are drilling down in, making mile-long cores of ice, and they're very carefully, counting and measuring the layers in these cores. They're extracting samples of the air from the bubbles trapped in these cores, trapped for tens of thousands, hundreds of thousands of years. They're pulling that air out in very tiny amounts. And so if you think about how much air you would get out of a layer like that, and how thick this ice core is. And what they're doing is they're literally counting the numbers of atoms in the air that comes out of these samples. So, one thing that I've heard, people who are climate skeptics say is that, it's difficult to determine with precision, what the climate variability is. And it's true, it is difficult to determine with precision what the climate is. But science does a lot of very difficult things. That's what science is about. Science takes careful measurement, and uses unbelievably precise and repeatable methods to learn things, from that information. So yes, it's hard to determine with precision, what the climate was in the past. But it's also hard to drill down through 1 kilometer of ice and extract a minuscule sample of ancient air and count the number of atoms in it. That's a really hard thing to do, but we are able to do that. We as society and as scientists, and that should be something that, when people say, oh, it's really hard, nobody really knows. Well, science does a lot of things that are really hard, and we just kind of accept that. It's really hard to, launch a spaceship into orbit, but we do it. And so, when people say, this is what we've measured, this is what we understand, it's not enough just to say, well, that's really hard. Nobody can actually do that. It was a little aside. All right, so that's how in a nutshell, how we try to understand the climate from the last, million years or so, 750,000 years. Prior to that, we, as I said, have to use less precise proxies, and because there's, the age of the ice doesn't extend for more than about 750,000 years. The next available proxy would be cores of sediments taken from the oceans. So if you think about the oceans, and this is something, if you take my oceanography class, we'll discuss in more detail. But if we think about the oceans, all of the material that erodes from the mountains and the land, a lot of that ends up in the deep ocean and settles down to the bottom of the ocean as sediments. And so the same sort of process of layering occurs in the deep ocean as in the these ice cores, except that the rate of sedimentation is like fractions of a millimeter per year in the deep ocean. So we can't resolve annual changes. In fact, we do well to resolve millennial or century-long changes. But some of the same processes can occur. So we can go deeper and deeper into this core. There are events that we understand that allow you to date cores relative to each other that come from different places. And so one of these examples is the PTEM, the Paleocene-Eocene thermal maximum. And that occurred right about here. This is the boundary between the Eocene and the Paleocene. And so, this is an event when there was very rapid change. This core doesn't show it, but there is another core. And so this PTEM occurred in about 55 million years ago. This coincides roughly with the cometary collision. So there's another core, and another core you would see the iridium layer that marked the impact of the comet. So big events, big changes do get preserved, and so we can see these very abrupt changes that signal some external process that was forcing climate. Okay. So these are proxy measurements, and so when we talk about change, this is how the information is acquired that lets us talk about what the climate was like in thousands of years ago or even millions of years ago by making these measurements. So what do we learn? What's the big picture by looking back on this? Okay, so here is 60 million years, 65 million years of climate change. Here's that PTEM event that I was describing to you. The KT boundary occurs right in about here, and so this green line here is the equivalent change in temperature, Celsius degrees, relative to averages. And so this line here, this dotted line here, represents a long-term average of temperature. And and you can see that the temperature has been declining steadily over the past 60 million years. That's what I was telling you about. And so in the Pliocene and Pleistocene, we can see that we were in relatively cold period, comparable to the previous tens of millions of years. So the take-home message here is that we live in a relatively cold period, a glacial period in Earth history. How do we know these things? Well, this is one of the proxy measurements. This is the O18. The oxygen 18 is an isotope of oxygen, and it's a proxy that allows us to understand the rate of precipitation over continents and at higher latitudes. And from that information, we can infer what global climate was. And so the benthic O18, that refers to the oxygen isotope composition of shells of organisms that have fallen to the floor of the ocean and been buried there. So this is a 60 million year climate record, and this 60 million year climate record is compiled from sediment cores. Okay? And some of those sediment cores record abrupt transitions like this PTEM. So here's the PTEM, this Paleocene-Eocene boundary, and previous to that it was relatively warm, and then there was a sudden warm spike, and then we proceed into this Eocene optimum, and then forward through time, and in the present time we're much colder than it was 60 million years ago. Okay. And then in this period here, this rapid glacial cycles, this describes, the last 3 to 4 million years. And within this last 3 to 4 million years, the Earth has been in a particular sort of mode where it's rapidly cycling back between glaciation and interglaciation. So the ice sheets are oscillating or varying between spreading across much of the northern and southern hemisphere continents and then retreating. So the advance and retreat, glaciation, interglaciation has been occurring relatively rapidly over this period of time. So the last, roughly 3 million years has been characterized by rapid glacial cycling. All right, now we've gotten forward to 100,000 years time scale. So here we are in the realm of the ice cores. And you have to think a little bit about how to interpret these graphs. So when it says 0, that's years before present. So as this graph, the numbers on this x-axis get larger and larger, we're going farther and farther back into the past. Okay? And so each of these, so these are all data that are collected from these bubbles of air that are extracted from the ice cores, and this is over the last 400,000 years. So this is essentially the Greenland ice core record. Well, what do we see when we look in this record, and what are we looking at in this graph? So the first thing we look, this blue line, is the change in temperature, delta C. And this change, so each of these changes, and this is being resolved with pretty high resolution, being displayed with pretty high resolution. So fractions of a degree per year can be resolved from these bubbles of air. And you can see, if you look at this, this is a very jagged line. It's going up and down. There are sort of fine scale variations that are occurring, at a 1,000-year time scale. 100-century time scale. But there are patterns. So this is the temperature going down and then up and down and up. And what you notice when you look at this there are periods of abrupt warming and followed by cooling. Okay, so how should we understand this? So remember that we're going back deeper and deeper into the past. So if we look at this spike here, this is the Eemian, I believe. It's a temperature event. And you can see that there's a sort of a rapid run-up in temperature. So the temperature increases quite rapidly over this period of a few thousand years, and then more gradually declines. And so that pattern of a rapid increase followed by a more gradual decrease seems to repeat itself multiple times in this record. And in fact, we're looking at it in a large scale here, but if you zoom in on any of these shorter term variations, you'd have a similar sort of display. So these are, warming periods. And we can see, if we look at this next graph, so this green line here is the CO2 content of those bubbles of air. And this is CO2 content in parts per million volume. So this is the content of CO2 measured by volume relative to the total volume of the sample. Well, one thing that's notable here is what kind of magnitude are we looking at? So this is parts per million volume. And so, the maximum amount of CO2 in the atmosphere, even in these very warming periods, was something above 280 parts per million. So something like, here maybe 310 parts per million, maybe 270 parts per million here, maybe 300 million parts per million, and so forth. So, and you can see that these spikes in CO2 fit pretty neatly within the spikes, certainly these major excursions in the temperature within this 100,000-year record. The other thing that you can see here is the amount of dust. And so there are particles of dust in parts per million. Not very much dust, but some dust is extracted. And the cold period, tend to be the time when the most dust is being deposited. So deposition of dust with this snow, and it's kind of a measure of how much snow is really falling, sort of lets us see that there are other, that, really gives us a measure, a proxy of precipitation in these periods. So that's at a 100,000 year time scale. Let's see. And so, just looking at this, we have to say, well, increases in atmospheric CO2 correspond with increases in temperature. And the problem is that we can't really tell whether this is a leading indicator or a lagging indicator from these data. In other words, does the increase in temperature cause the CO2 to go up, or does the increase in CO2 cause the temperature to go up? It doesn't really, it's not, you can't just explain that by the correlation between these two variables. But if we look at, all right, well, let's step forward then. Okay, so this brings us up to the present. And maybe I should show, well, I guess I'll talk about it, what the timescales are. So the thing to notice is that in the last 100,000 years, or the last few thousand years, the temperature has gotten relatively warm. And what are the other drivers in this? Well, let's step forward to the end of the last major glaciation event. So as I said, there was rapid expansion and retreat of the ice sheets that's been occurring over the last 3 million years or so. The last time this occurred was the last maximum glacial period was about 18 to 20,000 years ago, when most of the North American continent and most of Northern Europe was covered with huge ice sheets. In the Americas, the ice sheet was, the major ice sheet was the Laurentide ice sheet, and there was a little Cordilleran ice sheet, and in Europe, the ice sheet was the Drios ice sheet. And so these were sheets of ice that covered 18,000 years ago. You step forward to 7,000 years ago, and these ice sheets have largely disappeared. So that's the end of the glacial period and the beginning of the new period, deglaciation. Well, it doesn't occur, smoothly. There are changes. So there can be ice shelves and ice sheets. There can be places where, even when the land is completely covered with ice, where there are nunataks and places where the rocky mountain peaks are sticking above the ice. And these topographic changes allow different sorts of habitats and things to be included and to develop. But the retreat of this ice sheet, allowed sort of for primary succession. Remember, we talked about succession some time ago. So when the ice sheet was covering, so much of North America, there was obviously nothing but microbial life at the bottom of the ice sheet. When that retreated, the soils were opened and grasses and forest and woodlands and animals were able to, propagate out. Human beings were able to cross the Bering Land Bridge, starting probably 13,000 years ago, 12,000 years ago, and then move down into the North American continent. So this is, these are events that have occurred in the recent past. So the end of the ice cover and the beginning of this sort of more ice-free Europe and North American continent is a period in geology known as the Holocene. So this is the Holocene period. So the Holocene period begins, roughly with the end of the last glacial maximum, around 15 to 18,000 years ago, and then goes forward, through the present history. Well, A lot of people argue that we've reached the end of the Holocene, that we are now in a period called the Anthropocene. That's another discussion. But so most of most of civilization, and most of the way that we think about the ecosystems, the animal communities, the plant communities that we think of as being American or European or occurring in the planet are things that, situations that have evolved and developed over this last, roughly 10,000 year period. And during this last 10,000 year period, it's been relatively warm. So humanity has, human beings had evolved, and human beings lived on these ice sheets, and were able to develop, build tools and have society, make art, do all those things. But it wasn't until the ice sheets retreated that we really had the flourishing of human society. So our society and our species has developed during this period of relatively warm, benign conditions that followed the retreat of the Ice Age. Well, okay, so we've looked at all these different changes, and we've looked in particular at the last 3 or 4 million years, and we've observed that there are appear to be cycles of climate. Well, what is driving these cycles? It turns out, and this is something that was proposed by he wasn't Russian, he was, I think, Yugoslavian. Milankovitch was a mathematician. He worked in Russia, and as a mathematician back in the 20s, the 1920s, he proposed that the gravitational forces of the massive planets in the solar system, Jupiter, Saturn, Uranus, these planets were exerting a very slight but measurable influence on the orbit of the Earth around the Sun and the way in which the Earth was oriented. And so Milankovitch cycles were developed first as a hypothesis and then as a theory derived from understanding very precisely orbital mechanics and the way in which the orbital mechanics of the entire solar system would affect, in particular, the Earth. And there are 3 properties of the Earth's orbit around the Sun that are affected by the Milankovitch cycling. And this is something that you should learn. And the way to learn this is ETP. ETP. If you'll memorize this, and so when people talk about Milankovitch cycles, in your mind you'll flash onto ETP. Well, what does ETP stand for? E stands for eccentricity. So E is eccentricity. So ETP, eccentricity. And eccentricity is the tendency of the Earth's orbit around the Sun, which of course is not circular, but is an elliptical orbit, of this ellipse to elongate or constrict. And in this graph, this eccentricity of the elliptical orbit of the Earth around the Sun is hugely exaggerated. In fact, it's a very minor variation. And if you sort of drew a picture to actual scale of the Earth's actual orbital path around the Sun, to the eye, it wouldn't appear as an ellipse at all. So you barely are noticing the difference. But there is an eccentricity, there is an elliptical orbit that's measurable, and that is changing at a cycle scale of 110,000 years. So E, when our little memory device here, E is eccentricity, and you can also think of elliptical if that helps you remember E, and the number to remember is 110,000 years. Okay, so that's one thing, and you can understand that as the orbit becomes more or less elliptical, more or less eccentric, that the Earth is going to be relatively closer or farther from the Sun, and that would infer that we would be getting relatively more or less solar energy, more or less warming, and that variation in warming from the sun would have a period of about 110,000 years. So that's the E. What is the T? Well, the T stands for tilt of the Earth. Now we remember that the Earth is tilted at about 23 degrees. That tilt is varying within plus or minus about 2 degrees over this period of 40,000 years. So over a period of 40,000 years, the Earth is either more tilted or less tilted towards, and it's the tilting of the Earth towards the sun as it orbits around the sun that controls the amount of heat that arrives in the northern and southern hemispheres. So we have winter and summer in the northern hemisphere because when the tilt is toward the sun, the northern hemisphere tends to be warmer. When the tilt is away from the sun, the northern hemisphere tends to be colder. And that's happening on an annual scale. So we're going to have warm and cold seasons. Well, depending on how much it tilts towards the sun or away from the sun, that's going to control, the degree to which the seasonal variation will control the warming of the planet. So the tilt cycle is 40,000 years. So we've got E, eccentricity, T, tilt, eccentricity 110, tilt 40. And then there's a final cycle, which is precession. And in addition to being tilted, the Earth is wobbling a little bit, sort of like a top spinning, and the North Pole is sort of precessing around a circle. Now, again, these are, as it's drawn here, these are hugely exaggerated differences, for the purposes of illustration, but they are, and so. If you looked at these to scale, you would barely be able to see them. Well, you'd be able to see that the Earth is tilted, but you wouldn't see this variation in. So the precession cycle is 22,000 years. So Milankovitch cycles, ETP, eccentricity, tilt, precession, so 110, 40, and 22. Now, depending on which literature you read, sometimes it's 22, sometimes it's 21. I've seen 42. So the literature is not precise on the exact time scale, but 110, 40, and 22 is certainly the right ballpark for understanding these Milankovitch cycles. Okay, so what have we done? We've stepped all the way through climate cycles and looked at processes that are taking place at different scales over different periods, and we're seeing how there are external factors independent of the biology or anything else that's going on that create conditions, forcing conditions that would tend to favor temperature effects of one different variations. All right, what does this look like in terms of the temperature? So, this is time before present. So again, we're starting at 0 and we're going back at, at hundreds of thousands of years. And there's a change that occurs. So, prior to about 600,000 years ago, the Earth's variation in Earth's climate could be explained by the eccentricity cycle. So the variation in temperature prior to 600,000 years had about a 110,000 year cycle. After 600,000 years, we get into a tilt-dominated system. So the peaks here are about 22,000 years apart. Not perfectly, but close enough. So in review, before the end of the period here, let's go back and look where we're at. The Milankovitch cycles, 110,000 years, eccentricity, variation in the elongation of the Earth's elliptical orbit around the sun. So, and this is in time before present. So this is the eccentricity cycle, back 800,000 years. Here's the tilt cycle, and here is the precession cycle. So all three of these are operating at the same time and in different phases. And so eccentricity, tilt, precession. Time of the year when the Earth is closest to the sun. And over the last 800,000 years or so, the tilt cycle explains most of the variation that we're seeing. How does that look? Well, there are other things that are occurring here as well. This is temperature change, so this is back 250,000 years. So you can see here, that these, this is the precisions. This is the, yeah. So this is the. Then there are also cycles in solar cycle variation. So there are changes in sunspot activity, which are also driving that. Okay, well, I think I'll stop there, and I've packed in a lot of material. I haven't heard a peep out of anyone, so I assume that you've all been writing furiously and that you've achieved great understanding of this. But just in case, please ask me any questions about any of the slides that I've shown. Here, I'll switch the display around so that you can look back on all the slides, and perhaps that will spur you to ask some additional questions. So let's see. All right, so here are the slides that I've presented in today's
Dr.
lecture.
McDonald,
Yes.
I have a question.
Okay, Brittany, shoot.
So I don't think you ever mentioned a way that we're supposed to turn in the 5 quiz questions.
Oh, well, when you do your presentation, you'll have them written down and you'll email them or submit them.
Okay. Do you want us to add them in like a slide on the presentation? Would that be easier or?
That's a great way to do it. Yeah.
Okay.
But don't put the answer.
Right.
Okay?
Yeah.
Well, tell me the answer, or tell me the answer that you intend, but don't put it on the slide.
Okay. Thank you.
Sure. Any other questions about this material that I've talked about today? Darren.
Yes, I have a question about slide 9.
Okay.
You were counting the air lines in the core sample.
Yeah.
So what does that represent? It represents a year in time.
Yes, each of these is an annual year. So this is when probably.
Is that core actually? It slid in to the side like the guy's showing in the next picture over.
Yeah, they've drilled down. Here's
what it looks like when it comes out.
Yes, exactly. So here's the core top, and they drill down. They've got specially designed bits that drill into the ice, and they can pull a pipe out of that bit and extract the core, and then go a little bit deeper and extract a new core. And so they do that probably 10 feet at a time, more or less. And then each core comes out like that. It's very carefully numbered and frozen, high temperature, so that nothing is released. And then it's taken back to a special room, where they can slice it and they view it. There's this whole protocol for photographing it, for looking at these layers, and then for measuring where they are so they can correlate different cores with each other.
So that's like a 12-year-old sample then?
This sample covers 12 years, 12 annual cycles.
Now, could they have inserted it further and gotten more, or is that like as far thick as that ice is?
Oh no, this ice core, they will have when they finished drilling the Greenland ice sheets, for example, they ended up with nearly 2 kilometers of core, just like this.
Keep going back in the same hole, and
so they keep going back in the same hole, pulling out a new one, going back and pulling out a new one. It's a very laborious and precise process, but that's how they build up this picture. And I didn't want to, when we talk about scientists are just waving their hands and making stuff up. Well, no, this is really demanding and precise stuff. So thanks for your question. Hannah, did you have a question?
Yeah, I was just gonna ask, what do they do with the core when they finish? Like, does it just melt and they're done, or do they have a way of preserving it so like they can look back on it if they need to, or is there like what happens when they're done photographing and stuff.
Well, okay, that's a good question. In the case of the ice cores, I think that they're destructively sampled. So in order to get the air out, they have to slice the core. So they'll have to slice out this annual piece, and then they grind it up under very controlled circumstances, vacuum kind of conditions, and extract all the air so they get 100% of that sample. So that uses up the ice cores. Now I think they actually drill replicate cores or duplicate cores. So they've got one that they preserve and then one that they destroy in order to sample. And so I can't swear to that, but I think there is a permanent record. Now, in the case of the sediment cores, they don't take duplicates, but they slice them. So they'll slice the core exactly in half, and one half is put away as a permanent archive, and then the other half is retained. And there are different places. We used to have the Antarctic core facility here on campus in the old Carruthers building, or the basement of the old Carruthers building. But the funding fell through on that, and they don't keep cores there anymore. Now most of the cores that come from the ocean drilling program are stored at Texas A&M University in College Station. And so there's a big facility for storing those cores there. And people come from all over the world and work on that material. And they can take tiny samples of it, but the archive is kept as a permanent sample. Good question.
Thank you. I was also going to ask, I assume there's like no adverse effects of drilling into the icebergs, like they're not doing any potential damage by doing that?
I don't think so. No, I mean, no, no, I don't think it damages anything. It's not like the ice starts melting, and there's enough damage happening to the ice sheets of Greenland just because they're warming up. I don't think one core is going to make a lot of difference. But they do have to be super, super careful not to contaminate the cores with present day air or other kind of things, because of course that would mess up the sample. So this is done under super clean conditions.
Thank you.
Any other questions about any of the slides that I've showed so far? Yeah, go ahead, Berta.
So I wanted to ask, you talked in the slide 13, the cycle that controls the tilt of the Earth. You
Yeah.
talked about how when it's fully tilted, there is less of a difference in between seasons, which is a similar thing a similar effect that climate change is starting to have on our planet, right? Which there's less 4 different seasons distinction and more kind of like cold and hot. Is there a correlation in between those two? Like, are we at a point in which our tilt is at a certain point, or it just happens to be similar effect, but no correlation?
That's a really good question. And there's not a precise, simple answer, but fundamentally, we should now, given if things continued the way they had in the past, so if we stayed on the same rough cycle that we've been on, we should now be entering into a cold period. So if we use the past as a way to predict the future, we would now be going out of the interglacial and back into a glacial period. And so understanding of the Milankovitch cycles, and if climate was only being driven by tilt, then right now we're tilting more away from the sun, and so we should be getting a colder climate, so as you tilt more towards the sun, the difference between the winter and the summer become greater. As you tilt further away from the sun, the difference between the winter and summer become less. Well, we should be at a point when we're tilting away. And in fact, and this is one thing that climate deniers or climate skeptics will say, is they say, well, back in the 70s and the 80s, scientists were predicting that there would be a new ice age. And that's true. There were scientists who predicted back in the 70s and 80s that we should be entering into a new a cold period, because that prediction was based on Milankovitch cycle, and people were just beginning to understand the way Milankovitch cycles affect the climate. And the realization there was, oh, okay, well, if we look back in the past, we're tilted away now. We're in this period or this point in the Milankovitch cycle, so things should start getting colder. Well, they're not getting colder, are they? They're getting warmer. And so there's some other forcing factor that's coming into that, and that forcing factor happens to be, well, the best evidence is that it's, to a great extent, the amount of CO2 in the atmosphere, and then also the changes in land use patterns. So really good question. Not an exact answer, but that, that is, we should be getting colder, but we're getting warmer.
Yeah, but even though we are getting colder, we are having certain times a year. For example, I remember last year the record-breaking cold temperatures in some of the northern parts of the United States. So
yeah, all right, but now so that's that's a good question, but that's where you have to be careful, in leaping to conclusions. So the reason that meteorologists will say that the reason that we're getting these sort of global weirding, is another expression for that, is that the wind patterns, in particular the jet stream patterns, have changed because the Arctic is warming so much more rapidly than the rest of the planet, so that the jet stream, the Rossby waves that control the jet stream have become much larger, much more steep. And so you tend to get high periods and high conditions and lows. And so lows can become trapped and highs can become trapped. And trapped in the sense that they become stationary over part of the continent. And so in August and September, like California was under a heat dome. Well, a heat dome means that it was sitting under one of these stationary highs, which allowed temperature to rise.
okay.
And the same thing happens when you get these polar vortexes, which are like a low and a cold front that becomes stationary for long periods of time. And Milankovitch cycles figure in somewhere, but really the forcing factors are no longer, the Milankovitch cycles are still present and still affect the climate, but they're dominated by the stronger effect of global warming due to CO2 increases.
Okay.
And we'll talk about the mechanics of that in a lecture on Thursday.
That makes sense. So they're there and they have an effect, but they're not the main factor that will alter our climate, right?
Yeah. I mean, there's something that's more powerful that's pushing the cycle. I'm trying to think of a good analogy. It's like, I don't know, I'm not sure what a good analogy would be, but so the Milankovitch still has its effect. We're still tilting in the way that we, is predicted by, the orbital mechanics of Jupiter and everything. So we're still tilted the same way, but because there's this other forcing factor that doesn't have as big an effect on the climate and the weather as it would have done in the past when we didn't have that same forcing factor.
Right, when we didn't have bigger problems to worry about.
We didn't have bigger problems to worry about. Exactly.
All
Okay.
right, well, thank you, Professor.
Sure. And any of these other slides that you'd like to ask about? If not, any other questions? Okay, folks. Well, I will stop sharing here. These slides are on the thing there, and the book covers a lot of this material, but I think it's interesting to sort of dig a little bit more deeply into some of the processes that are, the book doesn't quite get to, and so that's why I want to present this. And we'll talk more about this on Thursday. Okay, everybody. Bye now.